Hello, this is Eric Campbell, and today I'll be presenting on Orbot, the hexapedal robot. I'll start with a brief introduction of myself and my advisor, Dr. Mark Plechnik. I'm a recent graduate from the University of Notre Dame in mechanical engineering, and Dr. Plechnik is an associate professor at the University of Notre Dame and the faculty advisor of the Singularity Lab, where I built the Orbot. Orbot takes a lot of inspiration from the family of bug bots that was popularized in the early 2000s. Bots like the Stanford University Sprawlita robot that have a certain animal as their inspiration. In this case, it would be a cockroach for Sprawlita. Um, they have always been interesting and captivated people inside of the robotics community and outside of it. Even watching the Boston Dynamics dog robot fall over in YouTube videos has made people feel inspired and interested in robotics in a way that perhaps wheeled robots haven't in the past. It is for this reason that myself and my advisor thought it would be a great idea to make a legged robot as a starting point for novice roboticists. Speaking from experience, getting into robotics can be daunting for young people, such as students in high school or middle school. Robotics has a way of bringing in multiple different disciplines into a singular project that can make it seem like an unattainable goal to build one of these robots. It is for this reason that we thought the Orbot should be a simple but also exciting and fun design that interests people who aren't experienced with robotics and also teaches those who have some experience something new. The mission statement for the Orbot is to create a robot capable of being assembled by a wide range of people, without tools and in under 1 hour. This 1 hour time point would be something that we return back to later on in the design phase and was a very large part of determining whether we had succeeded or not. The design philosophy was to have cheap and quick manufacturing, a low part count, very easy assembly, and a simple control system. It was also very important that we didn't have tools in the build process to cut down on the part count and also to make things less complicated. At the beginning of the design process, a key component was identified, which was the leg. For this, we had to build a robust framework using forward dynamics and 3D modeling to come up with a kinematic solution using a 4-bar mechanism. Each of these 6 legs is a primary load-bearing component, and so they needed to be robust enough to carry this load, but we also wanted to cut down on the size of each individual component to cut down on manufacturing time and also to reduce the number of individual pieces that needed to go into each leg. As you can see to the right here is the kinematic solution. The green curve is the path that the leg traces out on each rotation, and I'll play this video that shows the motion. Almost all of the Orbot was printed on a resin printer, and most of the connections are snap fits to avoid using auxiliary connecting pieces. This greatly cuts down on the assembly time, and there's a foolproof symmetrical design so that people don't get confused when putting it together. All of the Orbot's 3D parts can be manufactured in under 9 hours, and the Orbot itself can be put together in under 30 minutes, which is well below our goal of 1 hour. One of the most outstanding features of the Orbot is the platform stability. Because of the alternating tripedal gate, the Orbot is in quasi-static equilibrium, which means that barring inertial forces, the Orbot would be perfectly stable. The Orbot also has built-in torque control due to the 4-bar mechanism at each leg, which means that the mechanical advantage at the lowest point of each leg's path will be at its greatest. The Orbot is capable of carrying 1.5 times its own weight, and as can be seen in the video to the right, it has a very low assembly time.